Let's review how do we obtain the VTH and the RTH in the deafening sorrow. So VTH, regardless if the circuit or the network has independent source or not, it is obtained at the open circuit voltage or open terminal voltage. To obtain RTH, there are several ways. The common ways is to distinguish if the network has independent source or not. So if the network does not have independent source, then we turn off the independent sources and the circuit becomes only resistor network. So we can use the parallel and series technique to obtain RTH. Now, if the network has independent sources, then we need to turn off the independent sources the same as we did for the network without independent source. And then we need to add an external voltage or current sources. This is one way to add external source. We can add a voltage source and then RTH equals to V0 divided by I0. Normally we choose V0 equals to 1 volt and RTH equals 1 divided by I0. We can also add a current source. So RTH equals to V0 divided by I0. So we need to solve V0 in this case. We normally choose I0 equals to 1 for convenience. Now let's look at how do we obtain VTH and RTH for terminal A and B for this circuit. This circuit contains a controlled source, that's the voltage controlled current source. So now to obtain RTH, we need to add an external source. We choose to add a 1 volt voltage source and then define the I, the direction of I in this direction, then RTH equals 1 over I. So now the question is to solve I. To apply nodal analysis, first we define reference node, that's here, and then we look at the nodes. We have here two nodes A and B. And notice that the voltage on node A is equals to 1 volt because of this voltage source here. So therefore we have really here that's 1 volt. So let's apply the KCL on node A. Current flow into equals current flow out to. So we define the current in this branch in this direction. You can define other directions, but be consistent by yourself. So current flow into, that will be I and plus 0.5 Vx. That's current flow into. Current flow out to, that will be, there is one here, current flow out to, that's equals to 1 volt divided by 10 ohm here. And then this branch current flow out to, that's 1 volt minus Vx divided by 2 ohm. And this equation can be written as I plus Vx equals 0.6. Now let's look at node B. Current flow into equals current flow out to. So we have here current flow into, that is 1 minus Vx divided by 2. So that's the current flow into from this branch. So 1 minus Vx divided by 2 ohm. Current flow out to, there is one in this branch, so Vx divided by 3, and then Vx divided by 6. From this equation, solve for Vx equals 0.6, and then plugging into this equation, we can obtain I. So I equals 0.1, so therefore RTH equals 10 ohm. To obtain VTH, we open the terminal. And then we obtain the open terminal voltage. So VTH is here, and recognize that VTH is basically the voltage here as well. Pay attention that we do not close the independent sources. We do not close the dependent source as well. So basically the circuit remains the same. The only thing we need to do is open the terminal to calculate the open terminal voltage here. So now the question is just to solve VTH here. That's the voltage from this terminal to this terminal here. We can use mesh or we can use nodal. If we use mesh, we have 3 mesh here, 1, 2, 3. And pay attention that there is a current source involved, so you need to form a super mesh. But if we look at nodal analysis, how many nodes we have here? 1 and 2, so 2 nodes. Apparently using nodal analysis may be a little simpler. So to apply a nodal analysis, first of all, we specify the reference node and then recognize the nodes. So we have V2 and we want 2 nodes here. Now we will apply the KCL on each node. Node 1. So node 1 here. Current flow into the node equals current flow out of the node. Current flow into, that's this branch. That will be 50 volts minus V1 divided by 3 ohm equals to V1 divided by 6. That's current flow in this branch. And then V1 minus V2 divided by 2. That's current flow in this branch. And that equals to this equation here. Now let's look at the node 2. Current flow into this node equals current flow out of this node. Remember, this is the open terminal, nothing flow here. So current flow in this branch, that's the same of current flow in this branch. That's the same thing. So now current flow into the node, that's 0.5 Vx. And then this, and then this current here. So this current is V1 minus V2 divided by 2. And then what's current flow out? Flow out, that will be V2 divided by 10. So solving this equation, we can obtain V1 equals to 0.6 V2. Now there's 2 equations, 2 unknowns. We can solve V1 and V2. And recognize V2 is equals to VTH because this is a nodal voltage. V2, this is a reference node. So therefore, VTH equals to V2. Once we solve V2, we obtain VTH. So for the short terminal current in the Norton's theorem, for the short terminal current, so this that will be this. So short terminal, that will be I of n. So short terminal current for Norton's theorem, that equals VTH divided by RTH.